In this video, I'm planning on going over the solutions for your midterm exam number 1. And so for the first problem, you were given a plot, and just draw that real quick. And then it looks something like this. You had the FA naught over RA naught, and you had X here. And then you had some sort of curve that looked something like this. And the question said the rate versus conversion for an autocatalytic reaction is given in the following figure. So in this figure, find a combination of two reactors in series, PFR and or CSTR, which would minimize the total volume to achieve a conversion of 0.7. The combination may include two of the same reactor or one type followed by the other. Place the reactor that would minimize the total reactor volume first. Report the two reactor volumes. So you can figure, just by looking at this plot, you can see that based on so you know that for a CSTR, the volume of the reactor is this multiplied by this. So basically the area. And so depending on, if you're putting a CSTR, then you would just go down this line, and like say you're right here, then it would be this. And then you remember that the reactor volume for a PFR was the area under the curve. So for this same spot, the PFR would be all of this. So you can just kind of eyeball this plot, and you can see right away that the smallest volume is going to be a CSTR here, followed by a PFR here, and you wanted a conversion of 0.7, so this would be your PFR, and this would be your CSTR. And then it asked you to calculate the volume of the two reactors. So the CSTR volume is just this area, so you would just take wherever you are right here, multiplied by wherever you are right here. And then for the PFR, you need to calculate this area. And so with these, a lot of times with a curve like this, I usually just calculate the volume in here first, or the area in here first, and then I calculate this area and divide it by 2 and then add it. So this problem should have been pretty straightforward. If you had trouble with it, definitely go back and review how to design the volumes or design these reactors graphically. So for number 2, it says you have a reaction A to 2B, so I'll write that down. So A to 2B, and is taking place in a constant volume batch reactor, so V equals V naught. It's a batch. The reaction rate constant measured at 50 degrees C is 0.05 per minute, so K is equal to 0.05 minute minus 1 at 50 degrees C. The activation energy of the reaction is 280 kilojoules per mole, so E is equal to 280 kilojoules per mole. And then it says, what is the final pressure in this reactor in 2 minutes? So P at 2 minutes equals question mark. If a mixture of A containing 30% inerts, so that means that Y A naught is equal to 0.7 because it's 30% inerts. And it's reacted at 60 degrees C and P naught equals 1. So P naught equals 1 atmosphere and T equals 60 degrees C. So then we can just start setting this problem up like all the other problems we've been doing. So the mole balance, the rate law, and stoichiometry. So the mole balance, or the design equation, and we know that this is a batch reactor, so we use this design equation, T equals NA naught dx over minus RAV, and we write down the rate law, which is minus RA equals K CA, and I can't remember, did it just say well, so I'm assuming that this is a elementary rate law. So then stoichiometry, CA is equal to CA naught 1 minus X. So then you just go through and combine everything like we have been doing, and then integrate this equation. So I'm going to erase some stuff real quick. So then once we combine all this and integrate, what we get is T is equal to 1 over K, the natural log of 1 over 1 minus X. And by this point you should pretty much know how to get this equation. So that's why I skipped some of the math steps. And so looking at this, we know that we need K. So we're given K at 50 degrees C, but we need K at 60 degrees C. And so we can do that with this equation, K T is equal to K T naught E minus E over R 1 over T naught minus 1 over T. And so then what we would do is solve this. We solve this equation for T at 60. And we know what K is at T naught. So then once we get this, we can plug that into there. And then we know the time, so we can solve this equation for X. So we get X equals something. I think it was, well, I don't have it written down, but you get X equals something. So, but the problem wasn't asking for conversion, it's asking for the final pressure. And so you can get that from this equation. V is equal to V naught P naught over P 1 plus epsilon X. And so we know that V equals V naught. We know what P naught is. We know that epsilon is equal to Y A naught delta, and that's equal to YA naught, which I erased, but we had already found is 0.7 because we know it's 30% inerts. And then delta is just this, the B over A minus 1. So I think that ended up being 2 minus 1. So epsilon is equal to 0.7. So then you can plug that in. We know what X is because we calculated it from here. And so you should know everything in this equation to solve for P. So for number 3, it says reaction A to B, and it's a reversible reaction. So you have A to B is carried out in a plug flow reactor. So you know that you have a PFR the equilibrium constant is 3, so you know that Kc is equal to 3. The reaction is taking place in a PFR to pressure of 8.2 atmospheres, so you know that P is equal to 8.2 atmosphere and 127 degrees C, so T is equal to 127 C. The forward rate constant, so Kf, is 0.2 second minus 1, and the entering flow rate of A, so Fa naught, is 5 moles per second. So then it says if the volume of the PFR used is 100 liters, you know V is 100 liters, find the conversion in the reactor. So we're looking for X. So then we can start setting this equation up how we have every time. So the design equation or the mole balance, rate law, followed by stoichiometry. So the design equation is this. It's just the equation for a PFR. So V is equal to Fa naught dx over minus Ra. And then the rate law and so since it's a reversible reaction, you have to go through a few steps to get the rate law, but since I've already gone over how to find a rate law for a reversible reaction, I'm just going to write it down. So it's minus Ra is equal to K Ca minus Cb over Kc. And then the stoichiometry is this. Ca, and so our rate law has Ca and Cb, so we need to write an equation for both Ca and Cb. So Ca is equal to Ca naught 1 minus x, and Cb is equal to Ca naught x. So then we can combine these into the rate law, and doing that we get minus Ra is equal to K Ca naught 1 minus x minus Ca naught x over Kc. So then we can pull the Ca naught out, so we get minus Ra equals K Ca naught 1 minus x minus x over Kc. And then we want to simplify, or we want to pull the x out of this. So if we do that, we get minus Ra is equal to K Ca naught 1 minus x over 1 plus 1 over Kc. If you remember from homework 3, we've seen this sort of equation before, and you can simplify your integral if you rewrite this in terms of your equilibrium conversion. And if you remember with the reversible reactions, you can get your equilibrium conversion by setting the rate equal to 0, because when you reach equilibrium, the rate will be 0. So if you do that, you get 0 is equal to 1 minus x over 1 plus 1 over Kc. And I'm going to change that to xe, because now we're solving for the equilibrium conversion. And so then you can rearrange this. So we want to solve for, well, we want to get an equation, because we can see this, and we want to get something that we can plug in for this in terms of the equilibrium conversion. So we know that 1 over Xe is equal to 1 plus 1 over Kc. And then we know what Kc is, so we can solve this for Xe. And it turns out that Xe is equal to 0.75. But I'm not going to plug the number in. I'm going to plug in this equilibrium conversion into this equation. So since this is equal to this, then we can plug this in there in place of it. So then I'm going to erase some stuff so I can write this over here. So then I was plugging this 1 over Xe into this equation for the 1 plus 1 over Kc. So I have the rate is equal to K Ca naught 1 minus X over Xe. So then I can plug this equation into the design equation and integrate. So if I do that, I have V is equal to Fa naught 0 to X dx over K Ca naught 1 minus X over Xe. And so then if I integrate this, I get V is equal to Fa naught K over Ca naught Xe natural log X equilibrium conversion over the equilibrium conversion minus X. And I'm going through this math kind of fast because this is identical to I'm trying to remember which problem it was on the third assignment. So if you're confused about this problem, definitely go back and review looks like it's number 3 on the third assignment. And when I went through the solution for this in my video for homework 3, I went through the math on this in pretty good detail, and this is pretty much the same math. I mean, you could literally just take the solution you get for that and use it here. So that's why I'm kind of skipping steps in the math on this. So if you're confused about how to go through this, then either go back and review the solutions for that assignment or the video I did. So we can simplify this a little bit further. We know that Fa naught is equal to Ca naught V naught. And so if we plug that in for this, then the Ca naught will cancel out. So then we have V is equal to V naught over K Xe natural log Xe over Xe minus X. And then we know everything we need to solve this. We're solving for X. We know what the volume is. We know what K is. We know what Xe is. And so we need to find something for V naught. So we know that V naught is equal to F A naught over C A naught. And we know what Fa naught is, and we can calculate Ca naught because we were given the pressure and temperature initially. So, or we were given the temperature and pressure for the reactor. So we know that Ca naught is equal to P naught over RT. And it turns out that was 0.25 moles per liter. So then you can put that in there, and you know Fa naught because it's given in the problem statement. So then you can calculate V naught, plug that in, and then you can solve this equation for X. And I didn't write down what X is, but you should have everything you need to just solve for X at this point. So for number 4, it says a second order liquid phase. So I'm going to write that down. Second order liquid is carried out in a CSTR. And you get a conversion of 40% with a volume of 50 liters. So when V is 50 liters, x equals 0.4. And your desired conversion is 70%, so you want x equals 0.7. So you're going to place a PFR downstream of the CSTR to get this 70%. So it says determine the volume of the PFR. So what you have is you have a CSTR that's going into a PFR, and we know that this one is 50 liters. We know that x1 equals 0.4. We want x2 to equal 0.7, and we're looking for the volume of that. So now we can just do this, we can go through this the exact same way we have all the other problems. So first we write down the mole balance, or the design equation. I'm kind of using that interchangeably. And so we want to do the mole balance for the PFR because that's what we're doing the calculation on. So for the PFR, it's V is equal to FA naught dx over minus RA. And so we need the rate. And so we know it's second order. So the rate is minus RA equals K CA squared. And then for the stoichiometry, we know it's liquid, so we know that CA is equal to CA naught 1 minus X. So we can plug that into there, and we get that this is K CA naught squared 1 minus X squared. So then we can plug this into here and integrate. And I'm going to erase some stuff real quick. We have V is equal to FA naught. And then since we already have a certain amount of conversion coming into this, like it's the second reactor in series, we know that we know that X1, normally for just a single reactor, we've normally been putting 0 to X, but in this case it has to be X1 to X2. So, and then dx over, and then if we plug in RA, K CA squared 1 minus X squared. And then we can replace the FA naught is equal to CA naught V naught. So we can replace that. This is CA naught. And we can also pull out the K CA naught squared. So then V is equal to CA naught V naught over K CA naught squared X1 to X2 dx over 1 minus X squared. So then that cancels. And so then if we integrate this, then we get V is equal to V naught over K CA naught multiplied by 1 over 1 minus X2 minus 1 over 1 minus X1. And then right away you can see that we have a problem. We want to calculate the volume, and we know what X1 and X2 are, but we don't know what V naught we don't know the rate constant, and we don't know Ca naught. So since these are constants, we can get these from the CSTR because we know everything for the CSTR, so we should be able to solve the CSTR equation and get these. And so this is one reason why I always start solving my equations like this, like writing down the mole balance, because then if you just start here, as you go through the problem, it'll start becoming clear what information you're missing and what you need to do to get it. So for instance, you write down this equation, and then right away it's like, oh, I need the rate. And then right away from the rate, it's like, oh, I need the concentrations. And then combine and integrate, and then right away it's like, oh, I'm missing this stuff. How do I get that? And so, if you hadn't, we've solved a few problems on the homework where you found information from a different reactor, where you found this information from a different reactor and then used it. We can go ahead and write down the CSTR mole balance or design equation. And so we know that that is V is equal to FA naught X over minus RA. And then I erased it, but we've already figured out RA. The rate is the same in both reactors, so we already know what the rate is. So we can just substitute things in, and so I'm going to substitute in Ca naught V naught for Fa naught. So Ca naught V naught X over the rate, which was K Ca naught squared 1 minus X squared. And then we can just cancel that out. And then we can rearrange this a little bit. So we have V over V naught multiplied by K. And if you remember the V over V naught, that's actually tau. So this is tau K is equal to X over 1 minus X squared. And then we know what X is from the CSTR, so we can solve this and we can get tau K. So tau K equals something. And then if we come back over here to the PFR we're trying to solve, then the same thing. We know that V over V naught times, oh, I lost a Ca naught in here. This is, yeah, Ca naught. This is actually tau K Ca naught is equal to that. So then if I come over here, V over V naught, which is tau, so K Ca naught is equal to tau K Ca naught is equal to this 1 over 1 minus x2 minus 1 over 1 minus x1. So then I can take what I calculated for this and just set that equal. So then I can do this. I know that the volume of the PFR multiplied by this, so V CSTR over V naught K Ca naught is equal to 1 over 1 minus x2 minus 1 over 1 minus x1. And so I wrote the volume of CSTR here because remember this is just a number that you calculated. So what you need to do to get rid of the volume of the CSTR, which is known, is divide this by the volume of the CSTR. So volume of CSTR, and so you have some number here, and then you just divide it by the volume, and so that'll cancel out, and so then you're left with this, and you know what this is, and you should have a number here, so you should be able to calculate the volume of the PFR. And I'll just write down some numbers real quick just so this is a little more clear because this was kind of tricky. So for instance, we know that the V over V naught the volume of the CSTR over V naught multiplied by K Ca naught was equal to 1.11. So what you would do down here is you have the volume of the PFR, which is what you're solving for, and you would multiply it by the 1.11, and then that's equal to all of that stuff. And you know what x2 and x1 are, so that should be clear. But what I was saying here is this number is including so it's including the volume of the CSTR. And so you need to divide that out. So then this would be divided by 50, and because 50 was the volume of the CSTR. So then you have the 1.11 over 50, and then this 1 minus x2. x2 was 0.7, so this would be 0.3 minus 1 over x1. x1 was 40, so this would be 1 over 0.6. And so you have everything you need. The volume of the PFR is just this divided by this.